Hello, everyone. Today we are going to have some tutorials in machine design, AM411, and we are basically going to do about 3 questions. And the purpose of these tutorials is that you and everyone else should be able to understand and know how to handle different types of questions on each topic and see how these can be handled in various situations. So if you know how to handle one, you should be able to handle others. And so the many important thing that you need to do is to know the concept and so on and so forth. So here is question 1. Question 1 states that a plate of width 1.4 meters and length 2.8 meters is required to support a tensile force in the 2.8 meter direction of 4.0 meganewtons. Inspection procedure will detect only through thickness edge larger than 2.7 millimeters. So the two alloy, which is in table 5.1 on page 260 of the recommended book, are being considered for this application. And for this, we say the factor of safety must be 1.3, and the minimum weight is very important. And so the question is which alloy should be used, and you have to take the stress intensity modification factor beta to be equal to 1.1. Okay, so let's get started. This question is based on failure due to static loading, and from here we know that this beta, which is equal to 1.1, is the stress intensity modification factor. Okay, so what we're going to do is, as we look at the solution, the first thing that we need to first is to estimate the thickness required to resist yielding. And so estimation of the thickness required to resist yielding is given by this formula, where rho is equal to P divided by WT, where this is the stress, P is the force, and the W is the width of the plate, and T is the thickness of the plate. And the table to be considered from the question is table 5.1, and here is a table 5.1, which is showing the values of KIC for some engineering materials at room temperature. And this KIC is the fracture toughness of the material. In other ways, we call this KIC the critical stress intensity factor. Okay, so you have materials like aluminium 2024, which has the fracture toughness of 24 megapascal and the yield strength of 455 megapascal. We have aluminium 7075, but our main area of interest is titanium alloy. We have two titanium alloys, and what differentiates them is the yield strength of these two alloys. Okay, so from this yield strength, we can know which one is a stronger alloy and which one is a weak alloy based on the yield strength. So the weaker alloy have a lesser yield strength than the stronger alloy. And so from this titanium alloy, we know the 910 megapascal yield strength for this titanium becomes the weaker alloy, and the stronger alloy becomes the one with the yield strength of 1035 megapascal. We also have some materials like steel, which will have also the fracture toughness and also the yield strength of such kind of materials. So this table 5.1, which we are looking at, simply gives approximate typical room temperature values for the fracture toughness, which we call KIC for several materials. And so, as previously noted in the lecture that we have had, this fracture toughness depends on many factors, and the table, which we are considering here, table 5.1, is meant only to convey some typical magnitude of fracture toughness. Okay. So for the weaker alloy, we begin now the analysis. We are going to get the yield strength from table 5.1, and the yield strength for the weaker alloy is 910 megapascal. and so we are going to get the stress, which will be the yield strength divided by the number, the factor of safety, and from the question the factor of safety is given as 1.3. So the stress now becomes the yield strength 910 divided by the factor of safety, which is 1.3. And when you do this, you are going to get 700 megapascal as the answer. So the stress is now equal to the yield strength of the weak alloy divided by the factor of safety. So that's what we have gotten now as the stress. The thickness, therefore, now will be equal to the force, and this we can get from this formula we add here to say the stress is equal to the force divided by the width and the thickness. So now, making thickness the subject of the formula, we can now get the thickness as the force P divided by the thickness multiplied by the stress. And the stress that we have here is the 700 megapascal. And so you're going to get the force, which is 4 times 10 to the power 6, divided by the width is 1.4 multiplied by the stress here. And so this gives the thickness of about 4.08 millimeters or greater. The thickness can be a minimum of 4.08 millimeters or greater. So that is for the weaker alloy. We now go to the stronger alloy. So the stronger alloy, from table 5.1, we saw that the yield strength of the stronger alloy is 1035 megapascal. And we can get the stress using the same procedures for the weaker alloy, where we have the yield strength of the material divided by the factor of safety, and this gives us 796 megapascal as the stress. And from here we can get the thickness. We have the force that is subjected to that material, and we have the width of that plate, and we have the stress that we have calculated from above here, and this gives us 3.59 millimeter or greater. So that is now we have tried to find the thickness for the weaker alloy and the stronger alloy using the same procedure as we did for the weak alloy to do for the stronger alloy. Next, we need to actually now find the thickness to prevent crack propagation. So the thickness required to prevent crack propagation, we are going to solve considering the factor of safety as unit. So the stress intensity factor, Ki, is given by the modification factor, B, multiplied by the stress. And from the question we have been told that we consider beta to be equal to 1.1, and so this stress intensity factor will now be equal to 1.1 multiplied by rho, and the rest remain like that. And when we go for the weaker alloy from table 5.1, we can get the fracture toughness. So I quickly go to table 5.1 where we can get the fracture toughness. So the fracture toughness for the weaker alloy is 115 megapascal. So we come here, so that is what we have as the fracture toughness of the weaker alloy. And we can now get the ratio, the strength to stress ratio, which can be used as a factor of safety in this case. So we're going to get the fracture toughness divided by the stress intensity factor to get the factor of safety. So for the weak alloy, we know the fracture toughness is 115, and we know that the stress intensity factor is given by 1.1. And from there, we can now calculate when we make this stress inside this formula for the factor of safety as the subject of the formula, so that this formula now becomes that where we have the fracture toughness divided by 1.1 multiplied by n as a way in which we can now find the stress. So this N, we said we use unit as the factor of safety when we are dealing with the thickness to prevent crack propagation, and so we replace this by 1, and the value of alpha is 2.7, which from the question we can get from the question as the procedure here says the inspection employer will take on through thickness edge larger than 2.7. So we get this 2.7 that becomes our A in that formula, and so we put that into our formula here, and we are going to get the stress as 1135 megapascal. Now this answer that we have here is greater than the yield strength of the material, which is 910 megapascal, and we know that the yield strength is the basis for the geometry decision. So for geometry decision, we use the yield strength of the material, and so because of this, we have found this as greater than this, now we need to see what we are going to get when we consider the stronger alloy, because this one was the weaker alloy that we consider. So we are now going to consider the fracture toughness of the stronger alloy and see what we come up with. So from the same table 5.1, for the stronger alloy, the fracture toughness is 55, and so you're going to get that 55 and replace it into our equation to find the fracture stress. And so we put that 55 there for KIC, and our stress becomes 542.9 megapascal. And this answer above is less than the yield strength of the stronger alloy, and the yield strength of the stronger alloy was 1035 megapascal. If that be the case, then it means because we are considering the yield strength as the basis for the geometry decision, so we are going to now use this stress to find the thickness that we can work with as we handle this kind of a scenario. So the thickness now becomes equal to the force divided by the width multiplied by the stress. Now this stress is equal to the yield strength divided by the factor of safety. So we're going to consider the factor of safety that has been given in the equation, and then the stress, the fracture stress that we have found here, divided by the factor of safety multiplied by the width 1.4, and then this into the force 4 times 10 to the power 6, and this gives us 6.84 millimeter or greater. Okay, so this analysis that we've done here shows that the fracture toughness KIC limits the geometry when the stronger alloy is used, and so a thickness of 6.84 that we found here or greater is required. However, when we use the weaker alloy, the geometry is limited by the yield strength, because we saw that the fracture stress we found was greater than the yield strength. So the yield strength of the material would limit the thickness of the geometry that we are dealing with when you are dealing with the weaker alloy. Okay, and so from there we can conclude that the weaker alloy leads to a thinner and lighter weight choice, since the fracture mode differ between the weaker alloy and the stronger alloy. Okay, so that was the question 1. We can quickly go to question 2. Okay, so for question 2, here is the question. You are required to carry out design calculations to determine the test load at which the machine frame will experience initial yielding, and this is what we have as question 2. You are a design engineer to our engineering services. and your company has been engaged to manufacture the H-frame from steel of an off-highway machine. Some of the material properties of steel are that the yield strength is 400 megapascal and the yield strength in shear is 250 megapascal. It has become necessary to carry out stress analysis in the preliminary stages. Therefore, when loaded in a test fixture, the stresses were found to vary linearly with the load. However, 2 points were found to be most critical on the surface with a 4 kilonewton test load. Stresses at these points were point A, so we have here at point A, the sigma 1 or stress 1 was 200 megapascal, stress 2 was 100 megapascal, and at point B, this is point B, sigma 1 or stress 1 was 150 megapascal and stress 2 was 100 megapascal, shown in this figure, which shows the stresses on critical points, critical point A and the critical point B. Okay, so you are required to carry out design calculation to determine the test load at which the machine frame will experience initial yielding, and this will be according to the maximum normal stress theory, the maximum shear stress theory, and also the distortional energy theory. Not only that, you are also required to briefly discuss the relative validity of each theory for this application. Additionally, considering all the information available, what is your best judgment and advice to the client of the value of test load at which yielding would actually be expected to begin? Okay, so that's the question. Very simple and straightforward. So for this question, we are going to consider this graph. So when you look at this graph, it has a lot of things that come to our attention. We have a load line here, a load line for A, we have a load line for B, and here we have something that is of interest of this line, which shows that we are dealing with the shear theory, the distortional energy theory, the Moore theory. So this graph will be considered as we handle this question. And for the maximum shear stress theory, the distortional energy theory, and the Moore theory, we are going to consider the bottom part of this graph, because we've seen all these lines and we have some guidance that this is the shear theory, the distortional energy theory, and the Moore theory. However, for the maximum normal shear stress theory, we'll consider the upper part of this graph. So we are going to consider this graph. So how do we handle this question now? So we are going to begin with the solution to question A, where we need to now use the maximum normal stress theory to carry out the design calculation to determine the test load at which the machine frame will fail. So from the question here, we have this as a load that has been given for the specimen 4 kilonewton, and so we're going to use this load for the specimen to help us find the test load according to the normal the maximum normal stress theory, the maximum shear stress theory, and the distortional energy theory. And from this graph, we know that there is also the Moore theory, but from the question it has not been asked. But according to what we are going to do as we analyze, then you will be able to even extrapolate it to the Moore theory. Okay, so we begin with A. For the maximum normal stress theory, you see that the sigma 1 with stress 1 and the sigma 2 plot on the graph will show that point A is the critical point. Okay, and so now we're going to see how the failure will be predicted. So if this is the critical point at this point, we are going to get our sigma A, when you go down here, it will be 200, and sigma 2 will be about 100, and so we're going to consider the biggest of these, and so we're going to consider that as what we're going to have as our sigma, where this is critical. Now, here is a catch. When you look at this line, it touches these lines here, and when you follow these lines here, they are passing through this point 400 megapascal. Therefore, what you are going to do is, for you to find the load, you are going to get the test load from the question, multiplied by the ratio of this maximum where we have divided by this one, which is bigger than the 100 on these two plots, the sigma 1 and sigma 2. So you are going to get this 400 divided by this 200 multiplied by the test load from the question, which is 4 kilonewtons. So that's what you're going to get. So for this, you are going to get the 400 here divided by the 200 megapascal. What you get here, which will be 2 multiplied by 4, gives you 8 kilonewtons. So that means you have finished the design for the maximum normal stress theory. For the maximum shear stress theory, when you look at this plot, this is the maximum shear stress theory. You'll see that when you plot sigma 1 and sigma 2 on this graph, the graph will show that the critical point will be point B. And if this is the critical point for point B, we're going to see that what we are going to have as our sigma 1 and sigma 2, the ratio we're going to get will be that 150. But for the normal stress theory, we got that 400 because of where this line meets, and then when you go down here, that is what we have as our maximum. But then where this line meets, the maximum shear stress theory, which is this one, is at this point. So at this point, you get what we have, that is our value there, 240. So we're going to get the 240 divided by 150 here, where we have a critical point, and the answer you get multiplied by the test load from the question. That gives you the load according to the maximum shear stress here, which is 6.4. You're going to do the same for the distortional energy. You're going to consider that line for the distortional energy, where it meets with this line where we have the critical point B. So you're going to get this 275 divided by this 150 multiplied by the test load, and that should give you the answer is 7.3 kilonewtons when you're dealing with a distortional energy theory. Peradventure, we are given to do with a more theory, we are going to consider at that point, and then we get this 290 divided by this 150 multiplied by 4 kilonewtons, and then we'll get the value for the more theory. Okay. Then from the question, we are also asked to determine the relative validity of each theory. So you're going to go through all of the theories that we have discussed, and then we are also told from the question that we can also consider all the information available, what can be the best judgment or advice to the client of the value of the test load at which yielding would actually be expected to begin. Okay. So for validity of each theory, we know that the maximum normal stress theory should not be used for this application, and this is because it only gives good result only for brittle fractures. Then for the maximum shear theory, it may be used, but it's not very accurate, and the maximum distortion energy theory will give the best result for this application, and so the yielding effect begin at a load of 7.3 kilonewtons. Now we can do the last question for this tutorial, and the question 3 is as follows. You are carrying design experiment on a simply supported stationary shaft, and this shaft is 50 millimeters in diameter, and the shaft is made of AISI 1060 hot rod steel, and you can check this from table A20 to see the material properties of AISI 1060 hot rod steel, and you can find this on page 1048 of the recommended book. And so this will give us the material properties for this steel. So the shaft is subject to a maximum bending moment of 3,000 Newton meter and a maximum torque of 2,000 Newton meter. All you are required to do is use the distortion energy field to find the factor of safety corresponding to failure. So the first thing that you do is you go to table A20 and this is table A20. From table A20, we know that we are dealing with AISI 1060, and the 1060 is here, which is hot load, and we know that the yield strength is 370 megapascal. That's very important. But first, you are going to now find the bending stress. After you find the bending stress, then you're going to find the maximum torsional stress. After finding the maximum torsional stress, then we're going to use the distortional energy theory to find the factor of safety. So for the bending stress, we know that it will be given by 32 multiplied by the moment divided by pi d to the power 3, and this is the diameter of the shaft. And so you're going to get your 32 multiplied by the moment, and from the question, the moment was the bending moment was 3,000 Newton meter. Since the shaft diameter is in millimeters, we're going to convert this into Newton millimeter, and we're going to get about 3 million Newton millimeter multiplied by 32 divided by pi multiplied by 50 to the power 3, and we're going to get the answer as 244.46 megapascal. From here, we are now going to get the maximum torsional stress, which is given by 16T, T is the torque, pi d to the power 3, and we do the same to the torque as we did to the moment here, and we find that the maximum torsional stress is equal to 81.49 megapascal. And from the distortional energy theory, we know that the stress equivalent will be given by the maximum bending stress squared plus 3 multiplied by the maximum torsional stress squared. And so we're going to get this value for the bending stress, put it there, you square it, plus 3 multiplied by the value for the maximum torsional stress, you square it, and after you find the answer here, you're going to get the square root of that answer, and you're going to get the answer as 282.28. Then you go back to table A20 to get the yield strength of the material. The material is AISI 1060, and the yield strength is 370, and so you're going to get the factor of safety as the yield strength divided by this value that we've gotten here as the stress equivalent, and so the factor of safety then becomes 370 divided by 282.28. All these are in megapascals, and so the factor of safety becomes 1.31. Okay, so we will end there today, and I hope these 3 examples will open your mind, and you also know how to handle certain type of questions, especially that now you know how to go about it. Okay, thank you so much. Please stay safe. COVID-19 is very real.